Assalamu alaikum. Muhammad Qaisar Ali is here, and now I will talk about this computer a little bit in detail. So, in the first video where I showed the computer SAP 1, it was designed in Proteus. So, I just showed that how that computer can add two numbers. There were just four instructions which that computer was able to understand. That was load, LDA, then there was instruction out, there was instruction halt, and the other instruction was, I think, add. Yes, so there were four instructions. But this computer, in that video, I told that I will come up with an advanced version of this computer which will be able to understand more instruction and will be able to do a little bit complex tasks as compared to that computer. So I brought some more functionality to this computer. I add some more extra circuitry. I also programmed I also made the logics in such a way that now it's able to execute 16 instruction. It can understand 16 instruction. I will show that instruction later, that what instruction those are. And another thing which I also did in this computer, over here you can see the flags. These were missing in the previous version. So over here we can now monitor the content of the A register. We can check its sign, we can check whether the contents are 0 or not, and also whether the carry is generated or not during addition. So it would be helpful for the conditional decision. Suppose if you are jumping somewhere on carry, or if you are jumping somewhere on 0 or on sign flag, so those instructions are based on these three flags. The conditional instructions are based on these three flags. So now we will go through this computer a little in detail. So over here at the top right corner we have, and let me tell you that this is not, it's not SAP 1, it's neither SAP 1 nor SAP 2, it's, I think, in between, I would say, between the SAP 1 and 2. So I just named it randomly QSAP, and now let's talk a little bit about its function, its circuitry. So this is the program counter, this is the W bus, and we have A register over here, then we have the adder and subtractor over here, then we have B register. Also over here we have some flags, a little bit circuitry for the flags which is connected to the A register directly, and also the carry flag is connected to the adder or subtractor. And then we have at the bottom right corner the out register. Also the two 7 segment LEDs are present over here as well. On the top left corner we have the clock circuitry for the computer, and over here we can see that how we can single step the computer, or auto manual mode, or run or program mode, or halt and reset. All the controls are fed into this clock module or clock portion, and the only one output, this is just provided to all the rest of the computer components. Suppose program counter, memory address register, or whatever, that all will be enabled through this clock pulse. It's a single clock and it's spread all over the computer. Then we have memory address register and RAM over here. Here we can see that RAM upper nibble is this one, and RAM lower nibble is this one. And we have over here memory address register over here, and this circuitry is actually for loading the program from the ROM to the RAM. Actually there are two ways to program this computer. One is through dip switches, which I will show you in a while, and one is through another method in which you write a program in a text file, then you decode that into machine code. You wrote the program in assembly file using that instruction, then you converted that to, or you assembled it to machine code, and the machine code will be also in hex file. I will show you that how it looks like. Then you upload that to this ROM file, this ROM. Then you upload that file to this ROM through this way. Already I have uploaded it, so no need. Then what you do, that you load the program from the ROM to the RAM, and that's done over here through these switches. So actually this circuitry is responsible for that purpose. What it will do, it will make sure that each of the byte from the ROM, all the 16 byte, because this RAM is just 16 byte, we have just 4 address lines, so we can address 16 byte of memory in this computer. So RAM is just 16 byte. So this circuitry will make sure that it will take each and every byte from a specific location and will write it to the RAMs. So in this way all the 16 bytes will be written to the RAM. After that we can start running of the computer, and at the bottom left we can see a very important portion of this computer. I would say the brain of this computer. It's the instruction register and controller or sequencer. So here we can see that it's instruction register upper nibble and instruction register lower nibble, and it's the T state counter over here, just a binary counter with some other combinational logic. And over here we have two ROMs. These are actually two ROMs, so both are fed with the same address lines, and they have two outputs. Both of them have individual outputs, so we can see that 8 lines are out over here, and 8 are 8 from the upper byte and 8 from the lower byte. So in total we have 16 control signals. So for a specific instruction we will have some specific control signals output over here. So this is the main thing in this computer, I would say the brain of this computer, which provides the control signals to all the components of the computer. Here we can see that increment program counter, load program counter. Then we have enable program counter, which will put the data of the program counter on the W bus. Similarly load MAR and so on. So this is basically the main thing in this computer, I would say the brain of this computer. And I think we have covered almost everything in this computer, and we also have seen that how to load program to this ROM and then run. Now let's load the program of adding two numbers. You guys can find the Fibonacci number program in another video in this playlist as well. So suppose I'm adding two numbers, comma, hex AC hex, sorry, I think, okay, now let's start simulation. Sorry, I made some mistake. AC hex, hopefully it will work now. View the simulation. No. What might be the error? Okay, so that's good. So I will reduce its frequency. So you may say what's going on. I will reset the computer. First I will load the computer with first I will transfer the program from the ROM to the RAM. After that I will run it. So okay, that's great. So first load the program, it's done, it's loaded to the RAM. Now I will put it in run mode, and we will observe that now it's in auto mode. Let's increase the frequency a bit, and let's reset the computer as well, and we can see that now it's running. And sorry for the laggy video, because the Bluetooth is not running in the real time due to a very extreme load on my computer. So actually there were two values in this program. We were just adding two numbers. Let me show those numbers as well, and we can check it over here. Programs QSAP, and this is the program. So I will show in hex and assembly format. So what it will do, it will load the A register with 3H and add 6H with 3 and displays the result. So 3H plus 6H should be 9H. So our result should be 9H, which we already have seen over here in the output over here. So it works fine. Now let me show you another method of programming this computer. Now I will go over here and circuit. So it's another version of this computer which we program it through dip switches. So sorry guys for inconvenience. Okay, so what here we will do, you guys can see that here is no ROM to which we can upload assembly, a machine code or binary code, which then will be transferred to the RAM, and then we will start execution. Over here we have to program it through dip switches. So for this purpose, what we have to do, suppose you guys wrote in a program, and suppose we assume that the program is the okay. So first you write the program this way, then you translated the program to machine code, which is this way, which is this one. Then what you will do, if you are programming it through dip switches, then what you guys have to do, suppose 2E is equal to, let me make it smaller. Suppose 2 is equal to, in binary it's equal to 00101110. So I will place 2E at address location 0. So what I will do, that suppose I am starting the simulation, I put it in program mode, then I provide 00 address to the RAM, and I have to write this above numbers, these bits to the computer like this way. Yeah, then what I have to do, I have to toggle this button which will write the data to the RAM. Now what I will do, I will increment it, and I have to feed the another yeah, it's 5F. Now I have to program the second location as well. Now we can see that it's written over there as well. So this is there, but it's very time consuming. That's why I provided the another circuit of this computer which will which will do this stuff automatically, and that's very fast. So I will now show how I made this computer. I will go through it a little bit. So over here, programs, these were the programs. You guys are more than welcome to write your own program for this computer, and also I would suggest and highly motivate you guys to do additional thing to this computer. Suppose you guys can increase its memory from 16 byte to 256 byte, because now we are just using 4 address lines, but where there 8 data lines are available. So you guys can also use that as well in multiplexed manner. Now let's see how I made these circuits. So I use the basic and a popular strategy, which is divide and conquer. So I did not just build this computer in just 1 hour. I divided the problem into parts. I made first A register, B register. I well tested it, and after that I made adder and subtractor, then clock module, then controller sequencer, memory address register, and so on. After that I combined all these things to a single here you can see how A and B register looks like. Okay, so after that I combined all of them into a single circuit, which resulted in that computer. So here now we will see how the micro instruction of this computer looks like, and we will also see how much instruction we have. So over here I have made this as an Excel file. So actually a computer instruction cycle consists of basically two things: a fetch cycle and then execution cycle. So fetch cycle is same for the, and I would also say that each instruction is divided into sub instructions, which are known as T state. So we can see that fetch cycle is same for all instruction. For every instruction, fetch cycle is the same. So in our case, our computer instruction is divided into 5 T states, 6 T state. So it can execute an instruction with maximum of 6 T state or 6 clock cycles. So the T1, T2 and T3, this makes our fetch cycle, and it's same for all the instructions. So here we can see that at time T1 or T1 state, what should be the output of the controller and sequencer. So over here, if we look towards it, these two nibbles are, this byte is the upper byte of the controller sequencer ROM, which I showed you. There were actually 2 ROMs, and this is the output of the lower ROM. So this is my design. I have these instruction in my computer now, which does nothing. Then we have LDI, load immediately data. So this instruction is followed with a data, and it will load that data to a register. Then we have LDA, which will load the data from a specific address of the RAM. Then we have STA, we can store data to address. Then ADI, it's addition. So basically you can add 2 ways. If you have provided your 1 byte data at a specific address in RAM, then you can add do indirectly addition, means that you can add the content of an address of the RAM with the content of a register, and this is direct addition. So through this instruction, what you can do, that you just directly feed that data to the adder or subtractor for addition. Similarly, we have instruction for subtract, then we have for subtract, but it's direct and it's indirect, or it's through RAM. The data should be present at some address, then you load that data to B register. The first one is present already in the A register, and you do the subtract operation. And over here the case is not that one. Here you just the data will be directly fed it to the B register, and the first operand will be an A register, so subtraction will be performed over here in this way. Then we have increment A, decrement A, jump instruction. These are the instruction about which I told you in the computer practice, which the time when I was showing the computer. So over here there were some flags. So basically those 3 flags are used in this instruction, in these 4 instruction, and jump on carry, jump on 0, and jump on minus. So these 4 instructions are totally dependent upon that 3 flags, those 3 flags. Then we have the 15th instruction, that's the outer instruction, which will display the content of the A register through the 7 segment LEDs. Then we have at last the halt instruction, which will halt the computer. So basically each instruction is divided into sub instruction or micro instruction. These are known as micro instruction. So this was the most, I would say, the toughest part of this computer. The designing, or I would say that making the combinational logic for the controller in sequencer. So that's a very tough thing. That's why I use the another method in which you can write your output, your desired output, controller and sequencer output. Suppose for T1 I need this output for each address, irrespective of the instruction. I need this at T1, this output at T1, these output signals from the two ROMs at T1, and similarly to T2 have these specific combinations or signals, and T3 as well. So I wrote this data to that ROM. So what actually a ROM takes, it takes the opcode from the instruction register. Suppose for LD, for NOP we have the opcode 0, for LDI we have the opcode 1, for LDI we have the opcode suppose 2. So it will take the opcode from the instruction register, and with combination with T states it will generate this output. So basically the address of the ROM will be opcode plus the T states. So when it's incrementing, suppose for the first T state, suppose it's 0, and also we are executing the LDI command, so the opcode will be 1, so it will be 001, and then times state should be all be 0. Then what would happen that at the 0 address, at the 0, I don't know what it becomes. So suppose it will be something like, suppose opcode for LDI is, let's consider LDI suppose. So LDI opcode is 0010, and then for the and then there will be T states. So actually we have 6 T state over here, so minimum we need 3 bits, minimum we need 3 bits. So this we can see that this will be the address which will be we will provide to the ROM, and as the T states are get incremented, the address of the ROM will change, and similarly their corresponding output will also get changed. So how to achieve this type of input output mapping? So I did perform this job with the help of a C++ program. I wrote that program which generated a desired output of the controller in sequencer for a specific instruction and for a specific time state in that instruction as well. Sorry. So here I wrote a C++ program, and through that I generated the convert file which I then uploaded to the ROM. So here we can see that this is basically the instructions, and over here we have T states. So at the first T state, what should be the output of the convert, and similarly for T2, T3 and T4. Maximum T states, over here we have 6 T states, and over here we can see that it's a quite lengthy program, and if I haven't used this program, so it was nearly impossible to generate that file for those ROMs with hands. You can see that it's almost 600 lines of code. Okay, so what way it will do that, it will generate the controller and sequencer output for each input address, and what would be address? It would be the combination of the T state and instruction of code. So over here I generated these two files for the two RAMs. One is for lower byte of the controller, and second one is the for the upper byte. So here we can see that it's almost more than 1,000 line, I would say. And similarly over here we have another byte as well. Then I uploaded these two files to the ROM to perform the job of controller and sequencer. So I think this was all about this computer. I'll provide all the data in a Google Drive. I'll provide the link as well. So you all are most welcome. If you guys have any question, I will make another video as well. And I am suggesting you guys to write your own program for this computer, and if possible also enhance its design as well. You can increase the memory limitation from 16 byte to 256. And as I have shown you in the previous video that I was able to write a program just in 16 bytes for this computer, which was able to produce or to generate Fibonacci numbers and displayed that numbers as well. So all of you are highly motivated to do practice it, and it was basically a fun project. When I was in third semester of my engineering at UET Peshawar, they offered us the course of digital logic design DLD. So at the end of that course, when I was having a little time at home, a spare time, I thought about this computer, and the inspiration was Bin Eater. Bin Eater, that's a very nice engineering guy on YouTube. So his 8-bit computer was inspiration for me. I just started building that computer. He built actually that computer on breadboards, but due to lack of hardware and resources, I thought that I should make this computer in Proteus. So I started, and I think within 3 or 4 days I was able to make a working version of this computer. So I would also suggest you guys to modify the design or do some improvements. So this is, I think I would say, this is all for right now, and inshallah we will talk about the questions if there were any in the future. Thank you. Allah Hafiz.